Hi folks, this is your professor again, and now we're going to be talking about the terrestrial planets. This is not a fun topic for me in that just talking about the planets without their context is sort of not that interesting for me. So learning details about each specific planet is sort of kind of boring to me. I always like to talk about the context of these guys. And in the similar sort of fashion, the Jovian planets as well. So during class, I basically, during my face-to-face class, I basically let you guys do the studying and find out what's interesting for you, and I tweak it a little bit. All right. Some of the important things to recognize about the terrestrial planets is that they're all, yeah, as we discovered last week, made out of metals and silicon and things like that. And they're mostly really dense and small, as opposed to the Jovian planets, which are rather large and fluffy. Mercury is the one that's closest to the sun. It is the one that shows the most surface features that have been caused by bombardment. So asteroids and that sort of thing hitting the surface. And it's kept that history essentially forever. As we'll see very soon, has had no resurfacing on the planet. Venus is about the same size as the Earth, as you all well know, and it has a thick, cloudy atmosphere. It's very different than the Earth. Mercury is very different than the Earth. And then Mars is also very different from the Earth. There was the possibility that life occurred on Mars. We're still trying to understand or find the evidence for that sort of thing. But basically, we are searching for water on Mars, and we probably have found it. And it's water that sort of characterizes life as we know it. So all three of these terrestrial planets are very different than the Earth. They have some similarities to the Earth as well. They all have a little bit of an atmosphere, or a lot. Mercury has a thin atmosphere. It's understood that as it's indicated here, all these terrestrial planets have carbon dioxide as being a major constituent, except for the Earth. And that's very, very interesting. Mercury has a lot of hydrogen and helium that is outgassing from the sun, in fact. And Mercury doesn't have much of an atmosphere. We'll see that in a little bit when we look at the greenhouse effect for these four planets. Okay, and here's what we have. This chart really does characterize the effect of the greenhouse. Basically, the more of an atmosphere you have, the more stability you have in the day versus night temperature, and also how the temperature increases. So you see Mercury here with a very, very low atmosphere. It's also very close to the sun, having a huge variation in temperature between their nighttime and their daytime. And then we have Venus right next to it, as far as distance away from the sun. But you see that because of the atmosphere, that the daytime temperature is almost 500 degrees Celsius. Actually, the nighttime temperature is that too. The variation between nighttime and daytime you can't tell from the change in the temperature. And then we have the Earth. It rises and lowers depending upon nighttime and daytime temperatures. And then Mars has a greenhouse effect too, and you see that its variation is a little bit larger than that from the Earth. And then we have the rest of the planets to fill out what's going on here. Okay, terrestrial planet composition. We talked about that a little bit before. Let's see, I believe this is a picture of one of our spacecraft on Mars. I think I've shown you pictures of what a Martian landscape looks like. And if you want to get an idea of what it looks like, just go to the Amboy crater out by Barstow. It looks exactly like this picture. So terrestrial planets are made out of rocks and metals, and we have chemistry going on, oxidation type chemistry. So essentially water is affecting these things, rusting stuff. The interiors of the terrestrial planets, as we talked about last time in regards to the Earth, we make assumptions about what the planets look like, and from those assumptions we then characterize what the surface ought to look like, and then we look at the surface. So we're going to do that with the sun as well. The sun is easier to understand in that regard than our planets are. But we basically say that the interior of the planets looks like the Earth. And we know the Earth very well because of all the sonar that the earthquakes are providing us. So given that, if the Venus looks about the same size, it's got the same sort of stuff in the center, a core, a mantle, and a crust, and we say all the planets look like that. And so far, our models characterize the surface pretty well. If they're small, they freeze out, as exemplified by Mercury and Mars. And if they're quite much larger, then they don't. Then the inner core is doing stuff, and there's convection between the inner core and the outside crust, and we do see that on the surface of Venus, but in a way that's different than the Earth, due to the atmosphere of Venus causing the surface to be so hot. Now, the exteriors of the planets, as you can see down below, are characterized differently and similarly to Earth. We see the effect of resurfacing on the Earth more readily on the Earth than the other planets, but we do see certain effects of that on Venus as well as Mars. Okay, and then naturally the Moon didn't have much resurfacing going on at all, except when an asteroid hit it with so much oomph that it tapped into the inner regions and melted the top surface to create the Maria. That sort of situation also occurred on Mercury. So these are the processes that do shape surfaces, and we know that on the Earth all these things happen, and we have similarities or evidence of things like this happening on other worlds. And we'll also see that not only with the other terrestrial planets, but also, say, the moons of Jupiter. Io especially gets resurfaced, and Enceladus gets resurfaced, and that's a moon of Saturn. Okay, so this resurfacing really doesn't work on the Earth, although here's a picture of the crater that you saw in the Planets movie. This is, let's see, the planet out by Flagstaff, the crater out by Flagstaff, meteor crater. Great name. And here's another picture of one. I believe this is in Canada. So Earth has the most changed surface, as you know, and Mercury has the least changed surface. But some amazing things happened. Okay, and basically what we have here is Mercury being so small, everything is dictated by its smallness. It had a core and it cooled off. It had things hit it, and because of the cooling off, then the outer crust contracted and basically broke apart. And they use the example of a drying apple here. Another example is if you've ever walked on a muddy surface and then watched how the mud dried out, and it sort of goes into little, it peels and cracks form in the surface. So that's the sort of thing that we're talking about here. Other pictures of Mercury here. This one up here is showing a comparison between Mercury and our moon. Notice all the cratering that we see on both entities. And then if we look over here on the upper right hand corner, we see what's called the Caloris Basin. A really huge catastrophic asteroid landed here, right? and sent actually shock waves all the way to the other side of the planet. Notice how big it is. It's like a quarter of the size of the planet. Really huge. And then there are evidences of volcanoes on this little beastie. A volcanic vent here giving rise that there's still a bit of energy still left in the old critter. And we also see here this effect of the shrinking apple, if you will. So we had the crust fail, and as you can see here, the crater here was created before the crust collapsed. So kind of interesting how we can see and age these events by looking at how these various features on the surface interrupt and with each other. It was discovered not too long ago by one of our flyby satellites that Mercury does have a magnetic field, which quite surprised us. We thought that the core of Mercury is entirely solid, but if it has a magnetic field, as we learned from how the Earth's magnetic field is created, then the inner core, there must be an inner core and an outer core that is liquid, and that really surprised us. What also is surprising is Mercury is so much denser than the Earth, say, for the same size. It is a little bit more dense, and basically the point is that 75% of the planet, or if we read here, 42% of its volume is essentially an iron core, of which, for the Earth, it's 17%. And if you recall, the actual inner core, the solid portion, is about the size of Texas. So this is one of these features that I talked about earlier in our formation story that we have to include as something that's odd, that's strange. And the way that it is explained is that we had a collision of two objects about the same size, and this whole history here is talking about that. We had two planetesimals run into each other, and what ended up happening is the mantle for the original Mercury got blown away, and the iron coalesced into what's left of the two planetesimals. Okay. Now the other weird thing about Mercury is that its orbit is tied very distinctly to the Sun. It's in a highly elliptical orbit for a planet, as evidenced by this ellipse here. This ellipse actually exaggerates the ellipticity or the squashed nature of this ellipse from reality. But it gives you a better picture of what's going on here. Let it be said, though, that if you read this material here, you basically have the spin-orbit coupling, and this is essentially caused because of the tidal effects between the Sun and the various sides of Mercury. So as you know, tides are caused on the Earth by the Moon, and the Moon pulls material from those regions that are halfway between the Moon and the Earth. Okay, and those regions that are close to the Moon, things get pulled towards it. So we have a high tide associated with where the Moon is, and then we have a high tide directly opposite. Okay, so the gravitational field there is weaker, so the bulge sits out far away from the Moon, and there's a bulge of water that's close to the Moon. The same sort of thing is happening with Mercury, and the same sort of thing is happening with the Moon too, is that there are a bulge that sits out close to the Sun, and that gets preferentially locked in step with its orbit around the Sun. So the daytime and the nighttime rotation of Mercury gets locked into step, just like the Moon's locked into step with the Earth. Basically, for the Moon, we only see one side. Okay, we don't have a spinning moon relative to the Earth. We always see one side. And in a sense, that's what's going on with Mercury. We'll also see this effect with Venus as well. Okay, so here we come to the next planet, Venus, and we'll pause here for a moment and we'll pick it up